Let us try to learn about the most popular isolated DC-DC converter used in many applications. Flyback converter. Flyback converter is based on the buck boost converter. The buck boost converter originally had one inductor, two switches and one capacitor. So this in the place of inductor we bring in a transformer as shown in the figure, and that becomes a flyback converter. And as in the case of buck boost converter, here the output voltage VO will also be less than 0 if the transformer connections are this way. But if you flip the connection of the transformer on the secondary side, we can get a positive output voltage as shown in the third figure. So please pay attention to the difference between dotted terminals in both the circuits. But many a times the switch S1 is connected after the primary winding of the transformer in this circuit in many applications. The reason for shift of the position of S1, change of the position of S1 can be explained like this. If you want to replace this S1, of course we have to replace this S1 using MOSFET or diode. Usually S1 turns out to be MOSFET. So if we need to connect a MOSFET in this particular fashion, if we want to turn on the MOSFET, we need to apply a positive voltage at the gate terminal with respect to the source terminal. Please note that the source terminal here is not the same as the negative terminal of input voltage. It is something different. That means you need a local current to circulate like this, and this circuit will have a separate ground, which is this S. This is one of the needs of isolated power supplies. So you'll need some additional circuitry so that you can generate an isolated ground, because we need to generate a positive voltage at gate with respect to another point S, not the input ground. This is the input ground. Whereas if you shift the position of MOSFET, if you bring in the MOSFET after the primary winding, the source terminal of MOSFET becomes the same as the input ground. And to turn on this MOSFET, it is enough if you impress a positive voltage at gate with respect to the input ground itself. So this will avoid the need of an additional isolated ground or the additional isolated power supply for operation. That is why this topology or this representation of flyback converter is the most popular. So this is the circuit of our flyback converter. There is a switch S1 on the primary side of the transformer, and the switch S2 is on the secondary side of the transformer, and S1 is on, S2 is off for a duration of DTS, and S2 is on, S1 is off for the remaining duration, and it keeps happening. What is our objective? Our objective is to find the output voltage waveform and also the input current waveform and the average values of both. As we all know that in any transformer, the input current or the primary side current and the secondary side current are related to each other. And how are they related? The relation is given by Ampere's law. And to understand this Ampere's law, it will be good if you draw the exact representation of this transformer as shown here in the second figure. A transformer is nothing but two windings wound on a core. Here we have one winding of N1 turns, the other winding of N2 turns, and AC is the cross-sectional area of the core and it is uniform, and mu is the permeability of the core material, and Lm is the mean magnetic length, the mean length of the magnetic path in the core. And what does Ampere's law say? First, Ampere's law asks us to consider a closed path. Let us say we consider a closed path like this. This is the closed path. And along this closed path, we need to travel, and from one point we'll start. And what do we look at each point? We look at the, of course, this loop has to be in the magnetic field, and we look at the magnetic field intensity vector at each point. Let us say the magnetic field intensity vector at this point is like having a direction like this and that much particular magnitude. What do we need to know? We need to know the component of this magnetic field density vector along the direction of movement. So that is this. That is what is given by this h dot dl. We also know that the dot product gives the projection of one vector onto the other. So we get that projection, or we get the intensity of magnetic field in the direction of movement. In the direction of movement at various points like this, 1, 2, 3, 4, like this, and take the sum of the magnetic field intensities at all these points. I mean the magnetic field intensity in the direction of movement. And when the number of points considered becomes infinitely large, the sum becomes an integral. So that is what is this integral h dot dl. And what does Ampere say? Ampere says that this integral is equal to the current enclosed by this loop. So if you are traveling in this direction, we should look at the current flowing into the sheet. If we apply the same Ampere's law along the mean magnetic length in this core, the integral becomes simply HLM. Why? Because the core is constructed such that the magnetic field intensity is uniform, and also its direction is normal to the cross-sectional area, always normal to the cross-sectional, the surface of cross-sectional area. So the dot product naturally becomes just the product, as the angle is 0, so it becomes HLM. And on the right side, it will be N1I1 plus N2I2, because any path that you take, any closed path that you take within this core, it will enclose both the windings, N1, the primary winding of N1 turns and the secondary winding of N2 turns. And how does this plus sign come? The plus sign come because of the winding directions, or the way windings are wound. If you observe this figure, positive current I1 and positive current I2, positive current I1 and positive current I2 will result in the same direction of flux in the core. In other words, currents entering the dotted terminals will result in the same direction of flux, or the currents both will add up together, will aid each other to produce flux. That is why this plus sign comes in the right hand side of this Ampere's law equation. We can relate this magnetic field intensity to the magnetic flux density. That means H to B, and we know B and H are related like this for any typical magnetic material. So if we neglect the saturation and hysteresis, we can say that the relation between B and H is mu, and that is where typically most of the magnetic circuits are operated. They are operated without saturation. So we can write the relation between H and B as H is equal to B by mu. So substituting that on the left hand side, you will get this equation. And flux density is nothing but the flux per unit cross-sectional area. So we get the third equation by substituting B is equal to phi by AC. Again, we have assumed that the flux density is uniform throughout the core, which is a valid assumption. And this quantity Lm by AC times mu is known as the reluctance of the core. And if you replace that, we'll get this phi times Rc, which is the reluctance of the core, is equal to N1I1 plus N2I2. So this is how the currents are related in a transformer. If the core has infinite permeability, the left hand side term will be 0 and the currents will be related by directly the turns ratio. In a regular transformer, both I1 and I2 are flowing at the same time. Some input current will be flowing, which is typically sinusoidal, and again the output current will also be flowing. But of course there will be a phase difference between those two currents. But in this flyback converter, we have a peculiar situation. In the first interval, 0 less than t less than dts, S1 is on, S2 is off, so I2 is definitely 0. And in the second interval, S2 is on, S1 is off, so I1 is again 0. That means in a flyback converter, in the transformer of a flyback converter, both windings do not carry currents at the same time. So if you have a core of infinite permeability, nothing will happen because I1 is 0 sometimes and I2 is 0 sometimes. The sum on the right hand side will obviously be 0 and the left hand side is anyway 0 because of infinite permeability. So this flyback converter operates because of the fact that the permeability of a magnetic material is finite. So you need certain current to establish flux, and that will be flowing in the primary winding for some time and in the secondary winding for some time. So we have known the relation between the primary current and secondary current, I1 and I2, in a flyback converter, and because of the way it is being switched, we know that only one of them is positive or one of them is non-zero at any given point of time. But we need to know about the other one, the non-zero current in each interval. That means what is I1 in the first interval and what is I2 in the second interval. How does I1 vary in the first interval and how does I2 vary in the second interval? For that, we resort to Faraday's law. And what does it say? Faraday's law states that the rate of change of flux linkage is equal to the induced EMF, and that is written here as V1 is equal to N1 d phi by dt. When is this valid here? The induced EMF will be equal to the terminal voltage if you neglect the resistance of windings and the leakage flux. So with that assumption, we can write V1 is equal to N1 d phi by dt. And what is V1 here? The voltage across the winding V1. It is simply V in the first interval. Similarly, in the second interval, V2 will be equal to N2 d phi by dt. And what is V2? When S2 is on, V2 is nothing but negative of output voltage minus VO, and our small dipole approximation says that the output voltage is approximated by its average value. That is why V2 becomes minus capital VO. And in both cases, one of the current is 0 in both intervals. So in the first interval, I2 is 0. In the second interval, I1 is 0. So by substituting the flux equation, phi RC is equal to N1 I1 plus N2 I2, we can get the relation between V in and the current, primary current, as V in is equal to N1 square by RC into dI1 by dt in the first interval, and minus VO is equal to N2 square by RC times dI2 by dt in the second interval. So we wanted to know how I1 and I2 vary in the first and second intervals respectively. So we have come to a point where something is known about the rate of change of I1. So obviously V in is constant. For a given transformer, for a built transformer, N1 is also constant and core reluctance is constant, RC. So in the first interval, dI1 by dt is constant. That means current I1 rises linearly. Let us say it starts with an initial condition and rises like this. And obviously in the second interval I1 is anyway 0 because switch S1 is turned off. And this repeats again in every cycle. How about I2? I2 will be 0 in the first interval because S2 is off. In the second interval, whether I2 falls or not or rises depends upon the value of VO, polarity of VO. It can also be concluded from the waveform of flux. So in the first interval I2 is 0, I1 is rising linearly. So the flux will start rising because flux is proportional to I1 now. In the second interval, if VO is also positive, then phi will fall. Why? Because I2 will fall. dI2 by dt is negative. But if VO is negative, the flux will increase further because dI2 by dt will also be positive and it won't result in any periodic steady state condition. So the flux has to reach to the same point and it should keep on going up and down. And when will it happen? It will happen only if the output voltage VO is positive. And how does I2 look like? I2 looks like this in the second interval. Of course, it is 0 in the first interval and in the second interval it falls. But if the flux is proportional to current I2 and if I2 is falling in the second interval, what is the guarantee that the flux falls exactly from the same point? It could start falling from another point. So this kind of jumps in flux cannot be there because these are points which says that d phi by dt is infinity. And to have this kind of flux jumps, we need to impress infinite voltage on the windings, which is not possible. So with finite voltages, the flux has to be continuous. That means the derivative of flux can never be infinity. So the flux starts falling from the point to which it has risen in the first interval. This is known as the principle of flux continuity and it is very helpful in the analysis of many isolated DC-DC converters. So from the analysis we have done so far, we know that current I1 rises linearly in the first interval and because of that flux is also rising linearly in the first interval. Let us say if the flux starting to rise from point X and it reaches Y by the end of the first interval, the principle of flux continuity says that it should fall from the same point, and the principle of periodic steady state states that the flux should reach the same point again at the end of one cycle. That means the change in flux in the first interval is equal to the change in flux in the second interval, and using that we can derive the relation between the average value of output voltage and input voltage. How do we do that? We know V1 is equal to N1 d phi by dt, V2 is equal to N2 d phi by dt in respective intervals. So we approximate d phi by dt by delta phi by dts because Vin is constant. So Vin is equal to N1 delta phi by dts and minus VO is equal to N2 times minus delta phi by 1 minus dts. This minus delta phi is because it is falling. So periodic steady state says that the amount of rise and fall should be equal. So VO turns out to be d by 1 minus d into N2 by N1 times Vin. And what is the voltage gain of a buck boost converter? The voltage gain of a conventional buck boost converter is minus d by 1 minus d in times Vin. Here we have flipped the secondary to get a positive voltage, and we have also added transformer, so the turns ratio comes into picture. That is how we can say that flyback converter is derived from buck boost converter, and it is an isolated version of the same. So we have calculated the average value of output voltage, but we haven't plotted the output voltage waveform yet. To do that, we need the current through the capacitor, because integral of current through the capacitor will give us the output voltage VO. And how does the capacitor current look like? The capacitor current IC is nothing but I2 minus VO by R, and by our small ripple approximation, VO becomes equal to its average value, so it will be I2 minus capital VO by R, and that is exactly same. The capacitor current waveform is exactly same as I2, except that it is shifted by VO by R in the negative direction. So the capacitor current is equal to minus VO by R in the first interval, and the secondary current minus VO by R in the second interval. And in periodic steady state, we know that the average current through the capacitor is 0. That means the shaded areas are equal. Now we are ready to plot the waveform of output voltage. How does it vary? It falls in the first interval. Why? Because the capacitor current is negative and constant, so voltage across the capacitor will be linearly decreasing, and that is what is seen here, the first interval. And in the second interval, the capacitor current is positive, so the voltage will rise, and that will repeat over every cycle. And what is the peak to peak value? We have already calculated the average value of output voltage VO, which is D by 1 minus D times N2 by N1 times V in. And how do you calculate the ripple, peak to peak ripple? You look at the first interval, delta VO by DTS is equal to minus VO by RC. It is nothing but C dV by dt written in the difference form. So our small ripple approximation means that DTS is much less than RC. That means the switching time period is much smaller than the time constant of RC, which is the same condition arrived at in the case of buck boost converter. We have looked at the output voltage waveform, and what else we will be interested in? We are interested in the input current waveform, the current drawn from the source. That is same as the primary current I1. So In is equal to I1, so it has the same waveform as I1. But we don't know its average value, we haven't calculated yet. And we also don't know the different significant points in the waveform. Like for example, what is the peak value, what is the maximum value, and what is the minimum value, of course whenever it is non-zero. And so these things need to be identified. Similar is the case with I2. So let's try to find them out. The peak to peak value of current I1 and I2, whenever they are non-zero, can be found using the same equations based on Ampere's law and Faraday's law that we discussed earlier. So Ampere's law gave us the first equation, like phi times the core reluctance RC is equal to N1I1 plus N2I2, and as we know, I2 is 0 in the first interval, I1 is 0 in the second interval, and using Ampere's law we can say that the change in flux is proportional to change in I1 in the first interval, and the change in flux is proportional to change in I2 in the second interval. And from Faraday's law, we wrote that V in is equal to N1 delta phi by dTs, and similarly minus VO is equal to minus N2 into delta phi by 1 minus dTs in the second interval. So using these equations, we can directly say that delta I1, the peak to peak ripple in I1 when switch S1 is on, is equal to V in times dTs divided by N1 square by the core reluctance, and delta I2 is equal to VO times 1 minus dTs divided by N2 square by the core reluctance. And we already know the relation between VO and V in. VO is equal to D by 1 minus D into N2 by N1 times V in. Substituting that relation, we can say that the peak to peak ripple current in I2, the peak to peak ripple in I2 is equal to N1 by N2 times delta I1. And if you observe the denominators of these two equations, N1 square by Rc and N2 square by Rc, they are nothing but the magnetizing inductances of the transformer as seen from the primary winding terminals and the secondary winding terminals respectively. And how do you calculate the peak value of I2, the peak to peak value of I2? We know that KCL at node A will give us I2 is equal to IC plus IO, and if you integrate on both sides and divide by TS, that will result in the average value of I2 being equal to the average value of IO, because the average value of capacitor current is 0. That means the average value of I2 is nothing but the average output current VO by R. And what is the average value of I2? We can directly calculate it from the areas because they are all straight line segments. So it is 0 for DTS and it is non-zero in the 1 minus DTS second interval, and the area under I2 in the second interval is sum of the areas of one rectangle and one triangle, and that is what is written here. So we can say from this relation that I2n plus delta I2 by 2 is equal to VO times VO by 1 minus D times R. We have already known delta I2, and for a given input voltage we know the output voltage if you know the duty ratio. So we can calculate the minimum value of current, the minimum non-zero value of current I2n using this equation. The average value of input current can be calculated by power balance. The average input power is equal to average output power. That gives us V in into I in average or I1 average is equal to VO IO, and that can be written as I1 average is equal to VO by V in times VO by R, because the average output current is nothing but VO by R, and by the relation between VO and V in we can write I1 average as D by 1 minus D into N2 by N1 into VO by R. But from the waveform of I1, it's again piecewise linear as in the case of I2. We can calculate its average value by simply the areas, and we will get a similar expression I1n plus delta I1 by 2 is equal to D by 1 minus D into N2 by N1 into VO by R. So we know the minimum value, minimum non-zero value of I1, and we know the peak to peak value. We can calculate everything else, the peak value, and if any other measure is needed for I1. So this is how we analyze the flyback DC-DC converter in steady state. Let us look at the switch realization in a flyback converter. We need to replace these generic switches S1 and S2 by MOSFETs or diodes. So we need to look at the current carrying and voltage blocking capabilities required for these switches. So let us look at each interval. 0 less than t less than DTS, S1 is on, and since input voltage is greater than 0, IS1 is greater than 0. That means the current flowing through S1 is greater than 0. IS1 is nothing but I1, the primary current, and S2 is off. That means IS2 is 0. The current flowing through switch S2 is 0. That means IS2 is again same as the secondary current I2, and the voltage across the switch S2 would be minus V2 minus VO. This is obtained by applying KVL in the secondary loop, and V2 is minus N2 by N1 times V1 because it's a transformer, and minus VO. So that will give us the expression for switch voltage VS2 as minus of N2 by N1 V in plus VO. That means if you have a positive input voltage V in, VS2 would be negative when S2 is off. Now you look at the second interval. In the second interval, S1 is off, so IS1 is 0 and S2 is on. That means IS2 is greater than 0, which is equal to the secondary current, and of course VS2 is 0 because we have assumed the switches to be ideal. Even otherwise it will be very small voltage. But what is the voltage VS1? Vs1 is the voltage that is being blocked by the switch S1, and that is equal to V in minus V1 by KVL again. And what is V1? V1 is V2 times N1 by N2. And what is V2? V2 is nothing but the negative of output voltage minus VO. So Vs1 would be V in plus VO times N1 by N2. So that will again be positive. So S1 is blocking a positive voltage when it is off, while S2 is blocking a negative voltage when it is off, with the polarities defined. The waveforms for Vs1, Vs2 are also shown here, which are dependent upon these expressions. Now given that the current carrying capability of S1 should be positive, so S1 should be carrying current in downward direction, and it should be blocking a voltage in the off state which is positive. And in the case of S2, S2 should be carrying a current towards right when it is on, that is positive current, and it should be blocking a negative voltage as defined when it is off. So naturally S2 can be replaced by a diode, and S1, in the place of S1 we can bring in a MOSFET which has the required voltage blocking and current carrying capabilities. So this is how a practical flyback converter will look like. It has one MOSFET and one diode and one simple transformer and a capacitor. So that is why, because of this very low count of components, it has become extremely popular and widely used in many industrial applications. But what is the drawback? The drawback is that the input current is not smooth. The input current is pulsating. The current drawn from the source is pulsating. It's not a pure DC current. And another drawback is that we need switches of higher voltage rating. You look at the voltage that is actually blocked by input side switch S1. It is V in plus N1 by N2 VO. So V in plus VO has to be blocked, and VO is again transformed by the turns ratio. Similar is the case with S2. So this larger voltage blocking requirement than the actual voltages and the pulsating current drawn from source are the drawbacks of flyback converter. However, the advantages such as very low component count and very simple gate drive make the flyback converter attractive, and that is why it is used in many applications. Another interesting feature of flyback converter, which is very useful and which made it very popular, is its modularity. One can simply add multiple secondary windings to get different levels of output voltage. And remember, all these output voltages have different reference points. The grounds of the output voltages are not the same. So for example, here we have 3 secondary windings with turns N2, N3 and N4. So our output voltages VO1, VO2, VO3 can be different, or the turns can be chosen appropriately. The turns ratios can be chosen appropriately so that the output voltages are different. This is a very useful and interesting feature which made flyback converter very popular.